Hello friends, good morning. This is Professor Chaubey's physics class under the heading Physics Made Simplest for CBSE course, for NEET students, for G examination, etc. We were talking last time also common emitter configuration transistor, and I explained the beta and alpha transistor parameters, and we got a relation between beta and alpha also. Now I explain one experiment which is done in the class also, and that is the common emitter configuration. Common emitter configuration of a transistor, characteristics of common emitter configuration. We plot some graphs in the common emitter configuration. So this is the NPN transistor, means collector, base and emitter. N, P and N. And as per rule, you know, we bias this base, emitter base junction forward bias. So that is the current flows. So emitter is a negative, N-type. So we are biasing by negative potential. So this current from emitter flows means electron gets a forward push. And remember that we are biasing base emitter circuit. So the emitter base circuit is forward bias, means emitter terminal is forward. And biasing by a variable potentiometer. We have a small battery and we make a potential divider using a resistor, and we take variable terminal and connect here. So this is the current meter, micrometer, and connected here to base. And this voltmeter is to measure the voltage between B and E. So this measures BE, and this measures micrometer current IB. So this is the emitter base circuit, forward bias. And this is the collector base, collector emitter circuit here, where collector emitter is, you see collector is always reverse bias. So this is the NPN transistor. And so reverse bias means it should be positive potential. So we have large battery from maybe 0 to 20 volt or 30 volt power supply, and we use the potentiometer, variable current here, and connect a milliammeter to measure current, because current here are of milliampere order. So IC is measured by this. And what potential we have applied here across C and E is measured here by BCA voltmeter. So this is the variable battery for the collector biasing, and this is the variable battery for the base emitter biasing. And now the characteristics are that while keeping the BCE constant, means voltage here constant, fixing this here, and see how this variation of by this BBE and IB, how the base emitter current varies by changing the potential between B and E. Look at the graph, as I told you that keeping CE constant means BCE, we set this divider here so that the voltage here BCE is say 1 volt, that is a minimum, and then put 10 volt or 12 volt or 15 volt, that constant. So I have shown two curves, one BC 1 volt, one BC 10 volt, and how the BBE, that is the voltage BBE, changing, keeping BCE constant, how the BBE is changing and how the IB is changing. So that IE is changing, the emitter current is changing. So that you can see that how the emitter current changing, that we measure, and through the micrometer, and we measure the collector current through the milliammeter, and we measure the voltages this here. So remember that we measure the currents, and here the base current here, microampere here the base emitter potential, and we see the how base emitter potential, and this current is depending that I have probably this mistake. I am not. This must be IB, because IB current. So this is the experiment where we plot this graph, and from this graph we calculate. From this graph we draw the tangent at any point, and we calculate the delta of BBE, means delta of BBE means this side, and delta of IB. So at the here maybe say we draw a straight line here, and say just this any region. So this is delta of VE and this is a delta of IB. So by this, for the two, we can calculate for the straight line portion, it is constant. Curved portion we don't calculate, it is not constant. So the straight line portion, we get delta BBE over delta IB. And remember this we define because it's the voltage over current. So this is the units are of resistance. So this is defined as the input resistance Ri, and the value of this Ri is few hundred ohm. Because this depends of course on the base emitter. How much it is the junction and the N-type or P-type material, how much it is the doped in that material. So it is depends upon all the construction of the transistor, and that way we measure and we calculate the value of Ri input resistance by measuring this too. Okay, so this was one part of the experiment, and the other part of the experiment, so we have input resistance, and using the same circuit, I can now rub this circuit, but using the same circuit, and we can plot other graphs also. And remember that we can take NPN transistor or we can take PNP transistor. Just keep in the mind that circuit must be proper. Voltage applied, that is the emitter circuit is forward biased and collector circuit reverse biased. If you change the battery terminal, current will not flow. So this happens many times with the students in the laboratory, that current doesn't flow. They come to teacher, sir, current is not flowing, transistor is not working, it is bad. But actually, the potentials are not properly applied. So check the potential terminals of the battery and then see. Now this input resistance is measured. Well, you can have output characteristics also. Means it is the characteristic between collector current and the BCE. So another characteristic is we have input characteristic where we measure Ri, and then we have output characteristics. So what are the output characteristics? We plot a curve between, say, the parameters. What parameters are there? The BCE and the IB. We measure the collector emitter voltage and we measure the current IB. That is, we measure the current what current? IC, that is collector current, and we measure BCE. At constant value of IB, means base current constant, keeping base current constant, and we plot this graph. The graph is, say, I show you the experimental curve. This side we have, say, BCE. This side we have, say, IC, collector current, a few milliamperes, and BCE is a volt. This is increasing like this. So BCE is on this side and constant IB. So this type of the curves we get IB is a constant current, IB. It's a 5 microampere. IB is a 10 microampere. IB is a 15 microampere. IB is a 20 microampere, and so on. So keeping IB constant like this, and we change the collector emitter voltage from the rheostat variable potentiometer on the collector side, and we measure the IC current. But we change IB in the input circuit, that is the emitter based circuit. We change IB by changing the potentials of the battery by slightly using rheostat. So IB is kept constant, and we get this type of graph. From this type of graph, we can calculate, we can find out RO, that is the output resistance. Output resistance is defined as, what is output resistance? Delta BCE, delta of BCE over delta IC at constant IB. IB remains constant. So add one particular. All these in this portion and then just here, it becomes really constant. Its slight slope is there, not 100% parallel, but some slight slope is there. So delta BC over delta, we take, say, from this point to this point, we find out this delta BC, and we find out this delta of IC, and delta BC or delta here, because ratio of this, and we get the value of this upon this is the value of R0 output. But this output at constant IB. So this is some kilo ohms order. RI was input resistance few hundred ohms, and R0 output resistance is the kilo ohm. So we get this value. This is another important parameter of the common emitter circuit of the transistor. And the common emitter circuit transistor, you can see that one thing is here. In common emitter configuration, actual circuit, this is just to explain you, but actual circuit which is designed is where we use self-biasing and where we use not many batteries, but we use, say, only one battery. The actual circuit I make, which is used, is, say, I have here resistance coming to this. This is the base, the collector, and the emitter. So this here we connect here. That is the RC, that is the collector resistance, and here is the plus BCC. This is the battery line coming from the battery. So this is the battery, BCC source. That is the battery with the rheostat variable. So we apply voltage from here, and RC is the collector resistance. For the biasing of this base emitter circuit, what we do? We take self-biasing, which means we take resistances here, and we use two resistors here, and this we use the variable here. And here, this is the R1, and this is the R2, and we connect here and here we have capacitor, input capacitor, C in, and this is the R2 and R1, and here this is the error resistor, this is R3, and this is a CE, collector, emitter capacitance. So this circuit And here we have, say, at this point we take the coupling capacitor CC, coupling capacitor, to the next stage. And here we have, say, at this point and this point, this is the ground. This is the ground terminal or common terminal. So this is the output. And this is the input signal, input signal. Here, this is the input signal, and this is the output measure here across this point. So this is a circuit actually which is used for the where we don't use two batteries. Only one battery BCC gives the voltage to collector, and this using the resistance bleeder circuit here, series resistances, and making combination from here this voltage, and then this is the grounder. So current flows here and produces voltage drop here, and that is used for the biasing of the emitter and base. And this is the biasing for this collector and the emitter, and this emitter and base. And here we apply input signal, which, so this is actually circuit for common emitter amplifier. This is a circuit actually for common emitter amplifier. Here we apply a signal like this, and we get here output. Like this is the output. Voltage output, that is, say, this can be measured by the voltmeter, or this can be seen on the oscillograph also. Remember that this is common emitter amplifier circuit, one stage, single stage of the amplifier, and at this coupling capacitance, this can be used for the input stage just like this for the second. We have another amplifier, another transistor, and this is an input like this. And then output of that, we use again a capacitor, coupling. This is coupling capacitor. It can couple the third stage. So in this way, many stages can be connected. Several stages can be coupled through CC. So this is called RC coupled amplifier. Because resistance R is there and capacitance C is there. This capacitor is just like this capacitor, input capacitor. This acts as the input capacitor for the second stage, and then again another capacitor, the output like this, that is for third stage. So this amplifies signal, and whatever the ratio of output upon input is the gain. Gain AI is output upon input. So we get the gain. Maybe output upon input is 10, then it can be 10 stage, 10 output, 10 times amplified, and then this 10 coupled to second stage, and then it again 10 times means, so it becomes 100 times of the initial. Like this way, you can amplify your signal. Suppose it is 1 millivolt, second stage becomes 10 millivolt, then 100 millivolt, and then so on, 10 times multiply. So you can multiply your signal, you can get high signal, maybe volt, from millivolt to volt, or tens of volt. So this common emitter amplifier is very useful to amplify signal, and this is mostly used in all electronic circuits where we use common emitter configuration of transistor NPN or PNP, and we connect like this, and well, input here, and then we couple many stages, and then we get signal multiply. So that is the important thing, is that we get amplified signal, manifold amplified. So common emitter configuration is very important because it gives amplified signal, and by coupling many stages we get a manifold amplification of the signal. Well, I give you, I solve some value problem. Find the value of beta. That is, the beta is the coefficient of transistor. If 1 alpha is equal to 0.9, B or 2 alpha is equal to 0.98, C or 3 alpha is equal to 0.99, you can get beta. Simply you have beta alpha relation. Beta is equal to alpha upon 1 minus alpha. So that is the relation. So 0.9 upon 1 minus 0.9. This is for first part, and we get the answer is 9. Beta is 9. For second part, beta is equal to 0.98 divided by 1 minus 0.98. Well, this is about 49. And then next, third part, beta is equal to 4.99. 0.99, 1 minus 0.99. And for this, it becomes 99. So for different transistors parameters, alphas, this value, beta is this much. How much? Very large. Starting from 9 to 49 to 99. Okay. Similarly, we can have, say, calculate IE. Calculate IE, that is, calculate emitter current for a transistor. For a transistor, calculate IE for a transistor where beta is equal to 50 and IB is equal to 20 microampere. And this is, say beta is equal to 50, IB is equal to 20 microampere, means this is equal to how much? 0.02 milliampere. Okay. Beta is equal to, as per definition, IC over IB. Delta IC or delta IB, so this is simply IC over IB. And IC is equal to beta times IB. So IC is equal to beta times IB. Beta is 50, IB is 20. So beta times IB means 50 into 0.02. That is, IC is 1 milliampere. Now IE is IB plus IC. So that is, you add these two, 0.02 plus 1. So that is 1.02 milliampere. Like this you can solve, you can have examples. So this I have explained already, that transistor is an amplifier in common emitter configuration, and I tell you that the function working of transistor in common emitter C configuration is very good amplifier couple many stage we get RC coupled amplifier of high gain. One thing can you also notice, this is phase reversal. Means when the input pulse is positive, we get output negative, means fall of potential drop. When input potential increases, current it changes in the emitter based circuit such that it increases. So current increases means there in the collector circuit potential drop falls across the resistance, and hence it is the phase reversal. If current increases in the input circuit, current across this voltage drop, it decreases, and then it decreases, it increases. So there is 180 degree phase difference, a phase reversal, 180 degree phase change. So amplifier has got a phase reversal amplifier, means if this is the input, well output is like this. This phase reversal, this positive, this negative. So this is the output. And friends, well, I stop here now, and maybe on the next discussion I explain the transistor mode function as an oscillator or as a switch, and then on subsequent terms I will explain the logic gates, logic AND gate and OR gate, etc. So thank you very much.